Amy McGovern, thank you so much for coming on to talk about this important issue today. A lot of buzz out there. There's so much buzz when it comes to like private and public sectors right now too. So I want to get the stitch from you on everything going on, but can you give me a little background on yourself first and what your educational background is and then what you research right now?
Sure. So I'm a professor. I'm jointly appointed in meteorology and computer science. And so you asked for educational background. My PhD is actually in computer science. And I like to tell people I've been doing AI since before AI was cool. Because I think a lot of people seem to think that AI just appeared in the last few years, and that's not true. So my PhD was in AI. And then, I wanted to get into meteorology because it allowed me to do something that's interesting. And it lets me develop AI for a way that could save lives. And
Cool.
that's where I got into the meteorology.
Oh, good, because I want to talk about the history of AI in our country too, because like you said, it's gotten a lot of buzz in recent years, but can you tell me how long it's been in use and kind of the beginnings here?
It's been around a long time, since like the 50s and 60s, 1950s and 60s, so that's clear. It started with some really early systems they called like expert systems, where they were trying to do just help decision making in complicated decisions like healthcare systems. And they're really simple, like expert systems were rule-based systems. They were, can we codify sort of what's going on in the human decision making so that we can help them go through large quantities of data and perhaps remove some of the biases that are happening in these human decisions. So there were some of the early applications were in medicine. And then some of the other early applications, of course, have been in robotics, because robotics has been around a very long time too. And trying to make the robots do something more intelligent than be an RC system is a great part of AI.
Interesting. Okay, what about with weather? What about weather forecasting? When did that start?
So AI for weather. Weather's probably been around. So I've been part of the AMS AI conference for a while, and I think it started before I got out of grad school, so in the 90s, but they weren't meeting every year. They were just initial applications. And a lot of the initial stuff was basically taking the existing physics-based weather models and doing post-processing. It's no longer called that anymore. They have cool new words for everything. Post-processing is basically you take the physics-based model, you take the output, and then you try to correct the model biases, because those do happen. Everybody knows, one model has a cold bias, one model has a quorum bias, one model has spatial bias. So a lot of that was the early applications. And then people started to be able to dive into what can we do that's even better than that? Can we take the real-time data that's available and put that on top of the weather, the physics-based model, and try to give you a better forecast in real time, for example?
Okay. A lot of our listeners are probably not degreed meteorologists or scientists. So can you tell me kind of in layman's terms how AI is being used right now? Like if you're someone who's just looking for a forecast, maybe you pull up your phone every now and then, where are we seeing practical uses of AI in our forecasts now?
So that's a great question. I think that, the AI is happening behind the scenes. And so it's happening, most people are grabbing their smartphone and looking at the weather forecast, right? And what they're getting is a personalized forecast, right? The forecast is trying to personalize it for where they are. It's trying to give them a hyper local forecast. And that's being done with AI primarily, because what it's doing is back to that post-processing, trying to take the large scale model and try to downscale it, for example. It's happening in other places. There's the reason that AI is getting sort of hot right now is that you're hearing about these new global scale AI models, like Google's models and NVIDIA's models and all these other models. And you're hearing about them on the news and you're saying, wow, they're doing these great things. What they're really doing is AI forecast, AI-based weather forecasting across the whole globe. They're not going to, right now, they're not giving you something that's going to tell you where the next tornado is going to be. What they're doing is giving you a good idea of what the temperature is going to be. When's the next cold spell coming? When's the next heat wave coming? And those things they're doing really well at. And again, I think from the public, it's still behind the scenes. What's happening with those is those models are being used by the forecasters to put the human over the loop and give you a new forecast, but that's coming in as input to them. This latest cold freeze that just happened, I know this is airing in a couple of weeks, but there's a cold spell right now. And, some of the models didn't predict it to be as cold as it was. And if you go look at some of the AI models, some of them nailed it. And, that's a good question. But are they going to nail it all the time?
Very good question. So that brings up the point of specific types of weather. Do you see AI being successful with certain types of weather over other certain types of weather as far as research going on right now? Is there that possibility that it will predict where the next tornado is going to be or exactly where a hurricane is going to make landfall?
Those are excellent questions. And it actually relates to one of the things I'm doing outside of academia. So I'm consulting for a company called Brightband. We're a new startup company. And one of the things I'm doing there is developing a new benchmark suite called Extreme Weather Bench. And the goal is that we can enable people to evaluate them on the different types of high impact weather. So we have a whole tropical cyclone or hurricane section, right? And you can look and see how well it's doing at landfall prediction, how well it's doing at intensity of the hurricane, how well it's doing at the rainfall. But then you can also look at the severe weather. You can look at the flooding. You can look at the cold spell, so that you can actually break the performance up by the different categories of high impact weather. And I think that's going to be really important because right now, primarily the way people are evaluating them is they're looking at like the global root mean squared error. So they're saying, oh, well, on average, we're off by 2 degrees. Well, you know what? When it's 2 degrees off at 75, no one really cares. But when it's 2 degrees off, I'm sitting here just on the line of a freezing rain event, right? And the 2 degrees difference between 33 and 31 is a big difference in impact. Right.
Mhm.
And so an RMSE kind of obscures that, and having something that lets you dive into what the real impacts were, I think is good. And so the answer to your question is I think that the AI models are going to do well. We're already seeing in the news people looking at specific tropical cyclones, but they're not, when they do that, they don't tend to look at the other events. Right. So what we need to do is start diving into each of these high impact events and say, how well is it doing at that? You ask
Okay,
about tornadoes. Yes, I think that there are models in development that are working on those tornadoes. Are they ready tomorrow? No.
but it does seem that AI progresses much more quickly than like the science of the past. Am I crazy or is that true? Is it progressing really fast?
It is progressing really quickly. I don't know that it's that science of the past is slow so much as computers are getting faster all the time. So we're able to do things that we weren't able to do before. And the exponential growth in computer speed is enabling things to grow exponentially faster, right? You might have thought up, so the deep learning algorithm, for example, was thought up much earlier than it was actually been able to be used because the computers didn't exist for it. But as soon as they existed, people were able to just go.
What is your knowledge of what's going on with NOAA when it comes to the use of AI? Is there stuff in the works?
They have good stuff in the works. They have a NOAA Center for AI. It's a little bit different because of the way that NOAA is funded through Congress. They can get mandates to do something, but they don't necessarily get handed funding for that. And so
Yeah.
the NOAA Center for AI was created a couple of years ago, and they've really been working hard, but they were not actually granted an appropriations in the budget to actually fund them. And so they've been working with what the resources they can do. But they are doing a lot of AI throughout NOAA. And if you go to the NOAA Center for AI webpage, you can actually see a bunch of the applications of AI throughout NOAA. I mean, because I do have such close colleagues in NOAA, I see a lot of the things they're doing. They're testing these global AI models. They're testing the regional models. The tornado thing that you mentioned, there's a tornado model that's being developed that's actually based on Google's GraphCast model. It's called WAFScast. WAFS stands for Warn on Forecast model. So they're trying to make a GraphCast based version of the Warn on Forecast model. It's not operational, but that's another thing that NOAA does really well. NOAA does trustworthiness. They focus on making sure the models are trustworthy, and so they bring them up in test beds. And so all of these models that are getting tested are getting tested in the test beds before they go out and get thrown at the humans and the public.
You mentioned bias as far as warm air, cold bias, but I want to talk about other biases that occur when it comes to AI. Can AI be, and people can be this way too, can AI be biased against certain types of people?
Well, AI can, certainly. I think that's been in the news, right? The most obvious example is if you train the database on all white faces and you give it black faces to recognize, it struggles to recognize black faces. We have a paper that actually talks about how some of these biases can transition over to weather too, because you're not doing face recognition in weather. And so that's not an obvious translation. But there are ways in which those sort of societal biases that are happening do transition over. And that has to do with, for example, the data that you've collected. There tends to be more crowdsourced data in the more socioeconomic regions. But there's also just biases that exist in weather data that don't exist in other types of data. So physics bias. So the laws of physics apply to everything. But let me give you a simple one that's nice and easy. The radar goes out, like the Earth is round. This is where we need the video, right? Not just for the podcast listeners, but the Earth is
Your
round. The
description
radar is
is going
going
to
out
be
in a straight
amazing.
line. And when the radar goes out in a straight line, if you're trying to detect the tornadoes, the radar is only seeing the tornadoes, which are down at the lowest level nearest the radar. And so if you were training an AI model and it learned somehow that it had to see a particular signature in the radar, it might end up not giving you tornado detection farther away when that might actually be a problem because the radar coverage in the United States isn't exactly uniform everywhere. There's topography that gets in the way. And so you might deploy an algorithm that was only doing radar detection unintentionally really well in certain areas and not in others. And then people might have over reliance. This algorithm was great. It gave me 100%, every tornado, so trust it. And then it misses tornado.
Okay. Any other instances you can think of? Any specific examples?
Well, that one's my physics one because it's a nice, easy one. If you want some other examples, I'm trying to think of everything that's in the paper that we listed. So we had an example of how temperature forecasts are better in higher socioeconomic regions. And if you were ingesting that into your data, then that would be very different.
I read one that I think it was an interview you did that was about air quality and air
Yeah,
quality
air quality
sensors.
sensors are in that same thing because they're crowdsourced, right?
Mhm.
And any crowdsourced data has biases to it because humans have biases to it. We had a paper that was out that I'm referring, we've had two papers about biases. One of them is about categorization of the biases, and one that we haven't talked about yet that's going to apply to AI no matter what you're doing in AI is the biases that exist in our human nature. And that isn't to mean that we're bad. It just means that we humans make quick decisions. That's what psychology shows, right? And some of that comes from being overwhelmed. And we might be making quick decisions about data or how we process data or something that might make the data not as good for the AI model as it could have otherwise if we'd made it more careful. There's a book out there called Fast Thinking, Slow Thinking. And that's kind of what I'm referring to, that it isn't like it's inherently bad in us. It's just the way that we humans work. We have to make fast decisions when the cheetah is running out of us, right? But you want to make a more slow decision when you need to like ponder things. And sometimes when we're making these fast decisions, we're not aware that we're making the fast decisions. And so we might be making choices of metrics that aren't the best metric to actually check things. We might be making choices of how we process the data. We might be making choices when we're looking at model output and just saying quickly, I like that one, without diving into it deeply to understand where it is. Is that more
Yeah.
the route you were looking for examples?
Yeah, for sure. I guess I'm curious what the solution is then. Is it, more ethical training? Is it more variety of people working on the project? What's the answer?
All of the above. We've got a project that we just got funded and that we're working on developing some measurements so that you could actually ask your AI for weather model how biased it is in certain situations. Like, is it suffering from the physics bias? Is it suffering from a geographic bias? That's another example we could give. Like, you trained it all in the Southeast, but now it doesn't work all that well in the Northwest because they are very different weather regimes. So ask it these things so that you could then have a way to mitigate it. So if you had a checklist, then you could go through that and say, okay, now I can be more confident of that. So, but I think if you have the more people you have working on it, the more people you have are going to ask those kinds of questions. If you really literally only know the weather in one area, you're not even going to know that you're wrong in other areas.
Okay, so AI as a whole, when it comes to weather forecasting, what are some of the limitations other than biases? What are some of the other things you see as popping up as kind of bumps in the road going into the future?
I think a big bump in the road is data. And that is because the AI models don't actually know physics. They're learning physics from observations. And the observations they're getting are 40 or 50 or 60 years of data. Almost every model is training from ERA5. So that's ECMWF, the European model. They give out this reanalysis forecast that it's a great data set, but it's a coarse data set and it's known to have issues. The precipitation data isn't all that great. It's better in North America and Europe because we have more observations here. And so the AI models going forward, the big bump in the road is going to be how good can we make them everywhere when we don't have data everywhere, right? Can we make a great AI model for Africa when we don't have any data in Africa? Same for South America. We have some data, but not very much. It's a challenge. I think data is going to be the big bump in the road. We need higher resolution data and we need data globally everywhere. And even if we solved it, by the way, in all the countries I just mentioned, we need ocean data.
Mm.
There's a large part of the world that's ocean and it's not very well sensed.
Yeah, not just ocean. I interviewed a guy that's studying Everest and putting weather stations on Everest, and that's kind of another inhospitable environment that's hard to study too, right?
Very true. And it affects the rest of the world. That's the weird, like, people who are studying like something like, okay, I need my tornado and I need to know whether or not it's going to be here in the next hour in Oklahoma. I really don't care what it's doing in Everest right now from Oklahoma, right? But if I want to talk to you about drought in the next 2 months, I really need to know what's going on around the whole globe. And I can't just have these blind spots. And that's going to be something that we really need to address. I saw a really cool talk at AMS. This is not my work, so I'm promoting somebody else's work, but it was a really cool talk. Greg Hakem from the University of Washington gave a talk asking about what the limits of predictability were and whether or not AI could break the limits of predictability and that are known right now with the physics-based models. And I think that the talk he did was really cool because he was asking the question of, if you knew that there was going to be this really big event, how far back in advance could you get the AI model to predict it? And he showed that you could do it farther back than any of the physics-based models could do now. Now, it still requires you to know the right answer, but that's another thing that I see coming up. Is it like, how can AI break that current predictability barrier? How could we start predicting things 4 weeks in advance? And by the way, for the listeners, I'm not saying this is happening tomorrow.
So when is
This
it
is still
happening?
in development.
Any timeline at all? Are we talking
Yes.
months, years, decades?
Well, a timeline on that, years, but not in the decades. Not in the decades. I think that a lot of this stuff is going to be in the, especially because of what you asked at the beginning. AI feels like it's echoing exponentially. I think we're talking in the next couple of years, we're going to see some real breakthroughs on a lot of this.
Gotcha. Are there any unexpected uses for AI that you've seen come up that weren't really planned but have been useful when it comes to weather or climate?
NOAA has a couple of examples of those that I didn't really think about, and that's because I don't think as much about the ocean. So they have two that I've seen that I think are pretty cool. One is recognizing whale songs and whales and different whales, like a whale ID, not just songs, but like faces. And so you can actually figure out the migratory patterns of individual whales, which is just pretty cool because to me, it's a whale. And another one I saw that they've got deployed is riptide detection. And
Yes.
that's a place where you could save lives. It probably isn't unexpected to somebody who studies the riptides on a more regular
Right.
basis, but I live in
Yes.
a landlocked state, and I just thought it was cool. Because imagine that you could deploy that, and all the people that don't understand riptides, they could at least automatically have something on the beach that says, right now there's a high riptide, and you could visually show it. Here's where it is. Please don't go in. Because I think people sometimes don't always read the sign. Oh, that sign's been up since yesterday.
It's
Well,
funny. There's an upcoming podcast episode actually with Greg Dusek that I'm doing.
oh, awesome.
Yeah.
Awesome. He's
Okay.
certainly the right person to ask about that.
Yeah, he is the guy when it comes to that. Amy, is there anything else you want the general public to know when it comes to AI, what they should be looking for, what they should be wary of in the future when it comes to weather?
Well, I was going to ask, is that a general AI question or a weather AI question? Because the answer might be
Weather.
slightly different.
Definitely
Okay.
focus on weather.
Okay. It's an interesting question. I think a lot of the places that are out there right now are trying to make sure that they're testing what they're putting out, but I have a concern of that there might be people who are putting out models that are they're selling them, overselling them before they're ready because of the AI hype, and that is my concern and my thing to be wary of. I think that if you're running purchasing for a company, please make sure that what you're looking at is an actual model that's done a good set of evaluations. I think I'm not worried about that for the general public so much because I think the general public, the models that are getting deployed on your phone are getting pretty well verified because most people are getting them from NOAA, and NOAA does a really good job of doing verification and validation. But it's a concern for me that that somebody's going to predict the weather and people are going to die because it wasn't verified well, and that is it's a serious worry for me.
Yeah, it really kind of drills in the whole point of, the weather enterprise and the necessity of the, this piece of government, private sector, and academia all working together at this. So
Yes, having these collaborations and these partnerships is going to be really key to going forward, because that's another thing. You asked about a bump in the road earlier. Here's a bump in the road. NOAA doesn't have the computing resources that private industry does. Academia doesn't have the computing resources that private industry does. We need to find a better way to do those partnerships, right? Because academia can take a little bit more of the risks because that's what we write the grant, but like we're not selling the product. Whereas private industry needs to sell the product, but maybe we can do some of that exploration together so that it can actually be a great risk management strategy where we can do something really cool with the resources, but developing something that maybe somebody in private industry couldn't do it on a quarter basis. It's fun stuff. I'm very excited about the future of AI for weather.
Ilan Price, I want to talk to you about something that's getting a lot of buzz online right now, especially in my community, which is the weather community, the meteorologist community. And this was just kind of released recently, but Google DeepMind has done some amazing work when it comes to AI use of weather forecasting. So tell me about this latest announcement that you guys wrote about. What is GenCast?
GenCast is our new AI-based probabilistic medium-range weather forecasting model. And it's exciting because it is the first of these models that really outperforms the state-of-the-art up until this point, which have been weather forecasting models which use physics or simulate physics to forecast the weather. So it's an ensemble model. It's a probabilistic model, and it's an ensemble model. What that means is that instead of giving us one prediction of how the weather will develop, it gives us multiple scenarios. It helps us understand the range of possible outcomes, range of possible scenarios, and how likely each of those is to occur. And that really makes it much more useful for decision making. And in fact, the operational forecasts that we rely on day to day are ensemble forecasts like this. So we did a rigorous evaluation of this model, and we found that it outperforms this prior state of the art, which is ENS, which is the ensemble system from the European Center for Medium Range Weather Forecasting. And we found that it did better not just on day-to-day weather, but also on extreme weather, things like extreme heat, extreme cold, and predicting the tracks of tropical cyclones. And that's really, really important. It means, knowing these risks and the chance of these things happening earlier and being able to prepare better. And on top of being, a bit more accurate or more accurate, it's also much faster. So we're talking about doing in about 8 minutes on a chip that's a bit bigger than a laptop, what could take up to hours are for these traditional methods on supercomputers that have tens or hundreds of thousands of processors. So yeah, we really think that this is a something of an inflection point, a big milestone in the advance of this AI technology as applied to weather forecasting, because it's really the first time that operational, ensemble forecasts, the state-of-the-art forecasts that we could use operationally, that those are coming from AI-based methods, not these traditional physics-based methods.
So I want to kind of back up and talk about, a lot of our listeners are into science, but they don't have, a degree in science or a degree in computer programming. Can you kind of break down in really simple terms the difference between traditional computer modeling to do a forecast and the use of machine learning or AI to do a forecast?
Yeah, absolutely. No, it's a very important question, because they are taking quite fundamentally different approaches to predicting the weather. So the traditional approach to forecasting the weather is essentially to simulate the physics, or at least the dominant physics of the atmosphere. So what that means is that we write down some of the main physics equations that describe the way that the atmosphere develops over time, and then we use computers to solve these equations numerically, and that's a process which is a very computationally intensive process. But what it essentially does is simulate the physics, and we kind of roll the physics forward in time, and that tells us, okay, how is the atmosphere going to change? In other words, how is the weather going to change over time? And that's really fundamentally quite different to how an AI or machine learning based model would do that. The AI approach is not too hard to enforce any of the physics that we have written down. Instead, the model is going to look at historical weather data, basically decades worth of historical weather data, and we task the model, the machine learning model, with learning the weather patterns directly by looking at that data. So in simple terms, what we're going to do is we're going to say, give it what was the weather, at some day in 1980 on some Monday, and we're going to ask it, predict what was the weather how did the weather change in the next 12 hours? What was that weather 12 hours later? And then we'll show the model what really happened 12 hours later, and it'll be shown essentially what error did it make, and it'll make a little correction based on the mistake it made. And we're going to do that over and over again for data points over the last 4 decades. And in that process is what we call training the model. It learns to pick up, okay, if this is what the conditions were like, how is it likely that the weather will develop from that point? And so really it's learned directly from looking at kind of historical weather data or estimates of what the historical weather was, what these weather patterns are. And that's important because the equations that we solve, where the traditional models solve, they are really only an approximation to the full set of atmospheric dynamics. They don't capture everything. And machine learning models aren't restricted to learning those dynamics that we can write down in an equation. Because they're going to look at estimates of what really happened, they have the ability to hopefully learn more realistic and more complex dynamics than what those equations that we are solving describe. And that's fundamentally how it's possible that machine learning models can improve upon traditional models.
Okay, so what about current weather conditions? Because I always hear about, like they're flying into hurricanes and here's the latest data. So we're going to take this data and we're going to put it into the computer model and make the forecast better. So how does that work with AI? Do you use any current conditions?
So the historical data is really only for the learning process, to get the model good at predicting the weather. And then when we want to use the model to predict the weather, we use it in the same way, essentially, that we would use a current model. So we now tell the model, okay, you've seen all of this historical data, you've understood the weather patterns or learned how to predict the weather patterns. Here is the weather now. Tell us how the weather is going to change. And so you input what the weather conditions are now and what the weather conditions were, say, 12 hours ago. And then you get out of the model a prediction for what the weather will be over the course of the next 15 days. And as I mentioned, you don't actually get one prediction out. You get, say, 50 predictions out. And that is what we would call an ensemble of forecasts. And so it tells you, okay, these are the ways that the weather might change and allows you to calculate, okay, some things are more likely than others, but maybe there's a small chance of a cyclone going this way, and so it's worth preparing for anyway.
Okay. So let me get this straight. Let's say a traditional computer model is a college student. They're just taking like math and science classes, right? But like an AI computer model went to college and they took math, science, social studies, sociology, communications, and then they're both going out into the real world and kind of doing the same things, but AI is better prepared. Is that kind of a good analogy of what they are?
Yeah, in the sense that they are kind of exposed to different data, they're built with different data. There's a kind of, there's a truth in that analogy. Maybe I would say, the AI model didn't do maths and science.
A lot of
They
history though, right?
it
They were
just
big on the history.
they just did history, and they picked up, they basically learned the patterns of how the world changes. And the good thing about the weather is that for the most part, it's the underlying physics of the weather are fundamentally the same as they were over the course of this period of the training data period, the data that the model saw when it was learning how to predict the weather. And so we can verify, through this process of validating how well the model performs, we are checking that the kind of underlying processes of the weather are the same. And so it works to learn from the past and then predict in the future, because the fundamental patterns that it's learned are still true today, even though it was learned them by looking at data from the past.
Okay, so is an AI model going to do a better job of predicting weather in a changing climate then, because it's not having to go back and look at new physics all the time? Instead, it's just looking at like the past 20 or 40 years worth of data?
It's a really good question, and it's actually not something I'd say that we have a really definitive answer for. What I can say is that one of the main concerns, one of the chief immediate concerns of climate change is extreme weather, and so an important part of the paper that we published in Nature was an evaluation not just of the kind of average case weather over the course of the whole year, which we did do, but was also to look at how does the model do at predicting the risk of extreme weather, so extreme heat, extreme cold, and the tracks of tropical cyclones or extreme wind speed. And what we found was that even though the climate has been changing, and the weather in 2019 was not exactly the same as the weather in 1980, machine learning model GenCast, which was trained on this historical data, did still outperformed traditional models when predicting extreme weather. And so that tells us that, at least for now, these models are capturing the extremes well. They are predicting them well. They're predicting them better than traditional models. It's another important and good feature of machine learning models is that we can retrain them as we get more data and more recent data. We can keep updating them. So the model that we have in the paper was trained up looking at data up until 2018, and then we tested the model by using it in the future in 2019 and seeing how it did. If we want to make predictions now, though, there's no reason to stop the training data at 2018. We can use training data all the way up until yesterday, in theory. And so that allows the model to learn the fact that what the kind of recent weather patterns are, what is kind of more or less prominent and more or less likely given the most recent data. And we have verified that as you do that, as you include more and more data and more up-to-date data, that makes the model do better and better and better. That's another way in which the model can adapt.
Okay.
That being said, the reason I say it isn't an open and shut case. It's not. I don't say we have a definitive answer on that question. Is that if we reach, say, at some sort of tipping point, for example, where the weather dynamics really do stop representing what they used to look like, if the weather fundamentally changes in a way that historical patterns aren't really informative, well, then machine learning models will start to struggle more, because of course they're only really as good as the data that they're trained on. And so it's important that training data represents the circumstances that it's going to be used in day to day.
And then where does that data come from?
So the data that we train on is called reanalysis data. And what that means is it's basically an estimate of what the atmosphere was like in the past. And it comes from a data set that's called the ERA 5 reanalysis data set, which was produced, it's publicly available, and it was produced by the ECMWF, the European Centre for Medium Range Weather Forecasting. So that provides us with decades worth of estimates of what the weather conditions were like at different times, and that gives us our training data set. Now, when we evaluate the model, we can either use that data set to evaluate it, but we can also use the model real time. And to do that, we would feed in what we would call an operational analysis. So again, it's an estimate of what the atmosphere is like at the moment, rather than in the past.
We've had our fair share here in the U.S. This year alone. Hurricanes. Did you be able to apply this to any hurricanes that the U.S. may have experienced this year, or any specific storms? Maybe not this year, but I know the data goes back prior to 2019. Any specific, relatable that we can be like, oh yeah, we remember that it did really well with.
Yeah, absolutely, we did. So I could talk about Milton, for example, which was we did a retrospective analysis. So looking back, making predictions, in advance of Hurricane Milton, we can ask how would GenCast, how would this AI model have done if we were making predictions live in advance of the hurricane. So we could ask. So the forecasts allow us to calculate the risk of specific things happening because of this ensemble of forecasts. So we could ask questions like, according to the model, according to the model's predictions, what was the probability that Hurricane Milton would make landfall in Florida? And we can ask that question about forecasts that were made a day before, or 5 days before, or 10 days before that landfall actually did happen. And so we did that. We asked those questions about our model, and what we found is that 8.5 days in advance of that landfall, GenCast was predicting 60 to 80% probability of that landfall happening, and from about 5.75 days before landfall, it was predicted that landfall with landfall in Florida with more than 90% probability. And we could also, if we want to, we can open a map and we can look at what locations, landfall locations, are more or less likely. So, this is really that kind of prediction, 60 to 80% of probability of landfall about 8.5 days before it happened. That's actually even a few days before the hurricane formed. And that's, that sort of warning, that can be really important. Allows, whether it's preparing evacuation plans or stocking supplies, that could be really, really important. So that was I'd say a concrete case study that we did, looking at one prominent recent example and getting really good performance, really impressive advanced warning from GenCast about the tracks of these cyclones. But having mentioned that example, I think important to mention probably two other things, or caveats, so to speak. The first is that there's merit, but also merit in looking at individual case studies, but probably also worth taking each individual case study with a pinch of salt, because all models are going to do really well on some examples and slightly worse on other examples. And really, to make a scientific claim about the reliability of one's model, you really have to do a kind of extended evaluation of all cyclones over an extended period of time. So that's what we did in the Nature paper. So in our case, we took the full year of 2019 and we looked at all the cyclones and we compared our performance of the predictions of these tracks with the predictions made by ENS in that year, this state-of-the-art physics-based system. And so it's on that basis, that we are able to claim, okay, we're doing better at predicting the tracks of tropical cyclones, rather than on the basis of cherry picking a particular case study because we did really well in predicting Milton. So we have done that analysis. That analysis is in the paper. And then the second thing would be to bring up a limitation that GenCast and that this model currently faces, and that is that while it's currently really good at predicting the tracks of these storms, it currently doesn't do very well at predicting intensity of tropical cyclones. Now, the reason for that is essentially a function of the data that it was trained on. This ERA 5 reanalysis dataset that I mentioned, the training data that our model learns weather patterns from, those very extreme winds, very extreme cyclones, are not really well represented in that data set. And so the model doesn't really learn to represent them well. So we don't think that's an unsolvable problem. And we're confident that that's something we're going to be able to address. But it does mean that in the immediate term, the track predictions of models like this should be used in combination with other models that are better tailored to predicting cyclone intensity.
Gotcha. Okay, and you're talking about like the next step here and what you're going to do in the future, but the past was not that long ago, because I feel like it was just about a year ago I was talking to one of your colleagues about GraphCast and how amazing that was, and then here we are, this is now just a short time later talking about the next big thing. So this is really progressing pretty quickly, right? Can you tell me also the difference between GraphCast and GenCast?
Sure. You're absolutely right. The pace is really rapid. And especially if you think about the fact that, we got to where we are now with traditional models really over the course of decades. And that was really, and they have been fundamental in creating the data that has allowed this accelerated advance of AI-based models. They've now, based on that, based on those advances, based on that data that those traditional models created, really in the course of a few years, AI models have caught up and surpassed this decade's worth of research in traditional models, and now we have state-of-the-art weather predictions coming from machine learning. So really, the pace is very fast, and yes, the kind of gap between GraphCast and GenCast, the previous medium-range weather model from Google DeepMind and this most recent one, is also quite big. The fundamental difference between the previous model and this model is that the previous model was a deterministic model that gave us 10-day predictions. So it gave us a single kind of best guess at how the weather is going to develop. And that was a really important milestone because it really showed that machine learning models could learn some fundamental weather dynamics, and they could compete with single deterministic simulations by physics-based models. But even after GraphCast, the best operational systems, or even after our previous model was released, open source, the best operational systems were still using traditional-based methods, and that's because operational models have been ensemble models. They have to be probabilistic models because the weather is inherently uncertain. We can't predict it exactly. And so what we need to do is be able to predict the risks of different events happening. And that aspect of what's necessary for a really useful weather model, that's what our new AI model gives us. The fact that it's an ensemble model that gives us a range of possible scenarios and shows us what's more likely, what's less likely, and allows us to make sure we capture risks which are important even if they're small. Sometimes it's really important to know that there's a small chance of a really bad thing happening. And if you're only ever going to give the most likely prediction, you might miss that risk is something that you need to account for and you need to prepare for. So really, yeah, so that's there's multiple differences, there's a lot of technical differences and so on, but the kind of fundamental advance here over our previous model is to move to 15-day probabilistic ensemble predictions, which is really the thing that shows machine learning AI models are kind of ready for prime time in a sense. They're now ready to start being incorporated into operational weather forecasting systems and used alongside these traditional models.
It's really interesting what you said about conveying a small risk, even if it's really small, conveying that it exists. That's really I'd love to talk to like a social scientist about that and understand what the world would think of that. You mentioned hurricane intensity and wind speed. Are there any other weaknesses or limitations of the model?
Well, there's definitely opportunities to improve it. So, for example, there are certain variables, atmospheric variables, which the model doesn't at the moment predict. So, for example, it doesn't predict cloud cover at the moment. There isn't really a fundamental reason why it can't. We just didn't train it with that data. So the model could be retrained to do that. It could also further improve its resolution. So the model at the moment is a quarter-degree resolution model. That means that essentially we kind of divide up the world into these little squares. Each one is a quarter-degree latitude by a quarter-degree longitude. And then when we make a prediction for all of the different weather variables for each of the squares. And the smaller the squares, the higher the resolution of the model. And one option would be to train a model like this just at a higher resolution than what we've currently trained. But overall, I'd say it's a really overall, more or less across the board of all the different kinds of evaluations that we did across different weather variables, different levels in the atmosphere, different lengths of lead time, different types of evaluation, extreme, not extreme, calibration. So thinking about how reliable the forecasts are, and they're like, does it have enough uncertainty in the ensemble, in the set of predictions that it gives. Across all of these different evaluations, the model was overall better than the state of the art. So broadly speaking, a very strong set of results.
Okay, you talked about open source, and Google DeepMind's always been really good about like just sharing everything. Like, this is what we've done, this is what we have, we're putting it out there. But I'm curious kind of the why of that. Most people are in something to make money. And so I'd love a little background on like the ultimate goals of DeepMind and what the plan is here, because everybody thinks of Google as a search engine or their email. So what's with the science part?
Well, you're absolutely right that the team has a great track record of open source. In particular, the weather team here that developed our previous model, that model the code was made open source, the weights were made available for non-commercial use, so researchers could use them, could actually run the model themselves. And that was really important. There's hundreds, I don't know, maybe thousands of papers that are kind of building on using GraphCast, building on it both to advance research and to use it, as a kind of component of a larger system. So we really saw the kind of scientific impact of sharing our work like that. And it's something that's really important to the team. And we've done it again with this model. So the code is open source, the weights of the model, both the research model that generated the Nature paper results and an operational model that can be kind of run live. Both the weights of those are available for non-commercial use. And we've also just released an archive made available an archive of both historical forecasts made by the model and live forecasts that are being made by the model, which means that researchers can access, interrogate, do research on the outputs of these models without actually running the models themselves. And we think, we're really excited about that, excited about the fact that that's out there, it's shared with the community, they can test it, they can build on it, they can improve it. And yeah, it's important, firstly, to the team. We think weather is very much a public good, and we care about kind of advancing the scientific frontier in this regard. And that really, it squares very much with Google DeepMind's mission, which is to advance AI, for the benefit of humanity and the benefit of society. And this is one of those instances where machine learning can really have dramatic and very far-reaching benefits to everyone, because the weather touches everyone's lives, and in both small ways and sometimes life-changing or life-devastating ways. So yeah, we're definitely kind of excited and motivated by the fact that this sort of research can help advance a field which will really benefit so many people.
I really appreciate the time that you gave me. I think this is really important information for people to understand and get.
Thank you for having me. It was a great chat. Thanks a lot.